Hello friends. So in today's question we are going to solve questions that were asked in the 2018 and from 2018 we are having two questions from the mains and two questions are from advanced. So in total there are four questions. So first question that was asked in the year 2018 advance, and it states that in the xy plane the region y greater than 0 has a uniform magnetic field B1 k unit vector, and region y less than 0 has another uniform magnetic field B2 also k unit vector. A positively charged particle is projected from the origin along the positive y-axis with a speed v0 pi meter per second at t is equal to 0 as shown in the figure. Neglect gravity in this problem. Let at t is equal to capital T be the time when the particle crosses the x-axis from below for the first time. If B2 is equal to 4 times B1, the average speed of the particle in meter per second along x-axis in the time interval capital T is given as. If we are given the figure, so we have a, you can say, the magnetic field, and that magnetic field is B1 and B2. Direction of both the magnetic field is same. The only difference is the strength of magnetic field. So we can say that our for region y greater than 0, we have a magnetic field that is B1, and that is our magnetic field is B rather, or we can say it is B, and given as k unit vector, and for y less than 0 the magnetic field is B2, and that is also along our k unit vector, which is basically a positive z axis. And initial velocity is given as v0, and v0 is, you can say, at time t equals 0. And the important part is the relationship between two magnetic fields, which states that our B2 is greater than 4 times our B1. And it says that t is the time when the particle crosses x-axis from below for the first time. So we can draw an approximate, you can say, the circular path along which this positive charge is going to travel. It is a positively charged. So let us suppose this is our x-axis and magnetic field is along k vector. So initially it is given a velocity v0, and that velocity is along y-axis. So this is the initial velocity, which is our v0. So this is going to follow a semicircular path, something like this. And here the magnetic field is entirely B1, and let us suppose in this case the radius is our R1. And then we come to B2, and B2 is having the same magnitude. We can say the B2 is close to 4 times B1. So the strength of magnetic field B2 is very much large as compared to B1. So because of this, the radius of our R2, or we can say B2, the charge which is going to traverse it, will be much smaller as compared to our R1. So therefore, So this is our magnetic field B2, and we can just assume that, let us suppose this is the path traversed by the charge when it is in the B2 magnetic field, and here let R2 will be our radius. So because of this relationship, we can say our R2, which will be very much smaller than our R1, because the strength of magnetic field is very much larger than our B1. And we also know that the radius of circular path, we know the general formula, so we can write radius of circular path, and suppose that is given as small r, and that can be written as mv divided by q, that is charge, and multiply by magnetic field. And time period for you can say circular motion, time period of the circular motion is given as capital T, and that is equal to 2 pi m divided by q and b. And so average velocity will be equal to total distance traveled divided by total time taken. We can say average velocity is equal to total distance and divided by total time. So the total distance we are going to find out, and so let us do for one region, and we have a for region y greater than 0, radius is given as r1, so we can write this r1 will be equal to m v naught and q b1. Similarly, we can write for region 2, for region y less than 0, radius we said is our r2, and we go to this mv naught q, and this our magnetic field b2. The velocity in both the regions will be same, because the work done by the magnetic field on the moving charge is equal to 0. So velocity is not going to change. So it means the velocity at this point, same velocity will be available at this point also. Okay. So in this direction it will go v naught. And we know that our b2 is 4 times b1, so we can write here, so we get q, and this comes as 4 times b1. So we get the relationship between r2 and r1, so r2 will be equal to r1 divided by 4. And similarly, we can write for time period, so for because it is semicircle, so you can say for y greater than 0, t1 will be equal to capital T divided by 2, and this comes as pi m q by b1. And we can write for y less than 0, that is our t2, and that will be also can be written as pi 1m, and this comes as q and b2. Once again, we can write this as q pi m and this as q 4 times b1, and this gives us t1 upon 4. So this is the relationship between our t2 and t1. So if the total time is capital T, total time, let us call it as small t, then the small t will be equal to t1 plus t2. So this comes as t1 and t2 we know is t1 by 4. So we get total time t is equal to 5t1 divided by 4. And we already know that our t1 is our pi m upon q b1, and we substitute, we get this as t is equal to 5 pi m divided by 4, and this comes as q b1. And if required, we can also write in the form of a b2 also. Then we can write it later on if required. Next is our total distance. Total distance, let us suppose as d. So this d will be equal to twice r1 plus twice r2. We already know relationship between r1 and r2. So this gives us twice r1 plus twice into r1 by 4. So we get our d is equal to, this will be about twice r1, and here this 2 goes with this 2. So we are left with 4, and this comes as 5 r1 by 2. R1 by 2. And we already know that our r1 is our mv0, and we have this q b1. Therefore we can write that our d will be equal to 5 mv0, and this comes 2 q b1. So every speed will be equal to v average, and this we have our d upon t. We simply substitute the equations we just found out. So we can write this 5m v0 divided by 2q b1, and t we found out is 5 pi m, and divide by 4 q b1, and here m q b1 q1 cancels out. Okay, and now it's quite simple. So we can simply write v0 is given to us pi, so we can substitute it. So we get our v average is equal to this comes as, this can be cancelled, this goes by 2, 5 goes with 5. So we are left with v0 pi upon 2. So we can write this as 2 pi upon pi, and here pi goes with pi. So we are left with v average will be equal to 2 meter per second. So this is the velocity along, you can say, x-axis that was supposed to ask. Now we come to the next question. What was it? Okay, it was integer type. So next question, it was asked, it was asked in 2018 advance. So next question is also from the 2018 advanced question, and it states that two infinitely long straight wires lie in the xy plane along the lines x is equal to plus minus r. The wire located at x equal to plus r carries a constant current I1, and the wire located at x is equal to minus r carries a constant current I2. A circular loop of radius r is suspended with its center at 0, 0, square root of 3r and in a plane parallel to the xy plane. This loop carries a constant current of I in the clockwise direction as seen from the loop. And as seen from the above loop, the current in the wire is taken to positive if it is in plus j direction, j unit. Which of the following statements regarding the magnetic field B is or are true? So we are having four options, and we are going to find out which of them are correct and which of them will be incorrect. So we are going to take these options one by one. First option states that if the value of the current in both the wires, that is I1 and I2, are same, then the magnetic field cannot be equal to 0 at the origin, which is 0, 0 and 0. So let us test this option A. And option A states that current I1 is equal to I2, and it says that magnetic field is not equal to 0 at 0, 0, 0. So we have two wires. One wire it has plus x, another wire it has minus x. Okay. And we are going to find out what will be the magnetic field at the origin. So therefore, let us start with one wire, and so we can say field due to wires at the origin magnetic field due to wires at origin. We have two wires. First is our wire at x is equal to plus r. Let us suppose the magnetic field is given as B1, and this B1 will be equal to this relationship quite simple, that is our mu naught upon I1, and here we have this is 2 pi r, and the direction will be a k unit vector. And next we are having a wire at x is equal to minus r. Let us suppose the magnetic field is our B2, then we can write our mu naught I2, this will be 2 pi r and k unit vector, but the direction will be opposite, so this will be our minus of k2. Therefore the total field, a net field, because of these two wires, net magnetic field due to two wires, we can simply write the algebraic sum. So we can say magnetic field due to wires will be equal to our B1 plus B2. We substitute, only difference is in the current, and with negative sign they will be there. So we can write mu naught, and this is our 2 pi r, and here we can write I1 minus I2 and our k unit vector. and we satisfy the given condition which states that I1 is equal to I2. So we can write for I1 is equal to I2, the magnetic field because of the wire will be equal to 0. But we also has a loop at a certain height. So we can say field due to loop at the origin. Magnetic field due to loop at origin, and we can write this equation as magnetic field because of the loop will be equal to, this will be over mu naught I upon distance is given as square root of 3 times r. So this comes as 16r, and this is a k unit vector, and this is a negative sign. So it means the total field at origin, total field at origin, let us call that as B total, that will be equal to magnetic field due to wire plus magnetic field due to the loop. Magnetic field to the wire is 0, so the total field will be only because of the loop, and which is our minus mu naught I 16r, okay. And obviously that is non-zero, okay. So it means the statement A is correct one. You can say option A is correct. Now we come to the second B part, which states that if I1 is greater than 0, I2 less than 0, then B can be equal to 0 at the origin. So here for part B, the only thing will be because of the greater than and less than sign will be the direction of current. That's the most important part here. So we can go for now option B. And it states that if I have I1 greater than 0 and I2 less than 0, then it says that magnetic field can be 0 at origin. It doesn't specify the magnitude of I1 and I2. It simply states that for any value I1 is greater than 0 and I2 is less than 0. So this is the broader condition on the value of the current. So once again we start with the wires. You can say for wire at x is equal to plus r, in this condition current I1 is greater than 0. So you can say the current direction is our J unit vector. So the magnetic field, or we can say B1, is along plus k unit vector, and we can write its magnitude B1 will be equal to mu naught I1, and we have this as 2 pi r. Now we come to the second part, which says that for wire at x is equal to minus r, value of the current is 0. So now here the current direction will be minus of J. Current direction will be minus J unit vector, and the magnetic field will be along field at the origin rather. Okay, you can say the magnetic field at the origin is so my B2 is along plus k unit vector, and its magnitude I can write this as mu naught. Only consider magnitude of I2 divided by 2 pi r. So therefore total field due to the wires, total magnetic field due to wires B wires will be equal to B1 plus B2, and this will be mu naught upon 2 pi r, and here I have I1 and I2, and we have k unit vector. So it means B wire, the direction is along k unit vector, and the magnetic field due to the origin, the loop at the origin we just found out. So we can say B loop is equal to minus mu naught I upon 16r with k unit vector, and here the direction is along minus k unit vector. So it means if we only concentrate on directions, then we can say that the magnetic field can be equal to 0 at the origin, because the direction of net magnetic field will be, because of the origin, because of the wire it is plus k, and because of the loop it is minus k. So both the fields are in opposite direction. So it might be possible for the value of I1 which is greater than 0, or we can say for any value of I1 which is greater than 0, and for any value of I2 that is greater than less than 0, we might find that the magnetic field of the loop is equal to the magnetic field of the wires. That will be resulting in net magnetic field equal to 0 at the origin. So we can say that magnetic field due to wire is along k unit vector, and magnetic field due to loop is along minus k. So therefore we can write that magnetic field at origin can be 0. So this option is our correct. You can say option B is our correct. Option B is correct. Now we come to the option C. And it states that our now I1 is less than 0, and I2 is greater than 0, here also it says that net magnetic field can be 0 at origin. So now we can just write it straightforward that the direction of current because of the wire at x is equal to plus r will be now minus j unit vector. So we can write this as current direction due to wire at x equal to plus r will be our minus of j. Magnetic field that is our B1, this will be along our minus of k, and the magnitude B1 will be equal to mu naught I1, and this is our 2 pi r. Similarly, we can write that current direction due to wire at x equal to minus r. Now this will be our plus j, and magnetic field its direction of P2 will be along minus k, and our magnitude B2 will be equal to mu naught I2, and this comes to pi r. So total field due to the wire, so you can see B wire will be equal to, this comes as minus mu naught 2 pi r, and we can write this as I unit vector plus I2, and we have k unit vector, and direction will be along minus k unit vector, and for loop the direction is also, you can say it is same, that is our minus k unit vector. Okay. So it means the direction of the loop as well as direction of the wire is same, minus k unit vector. Okay. So it means B, that is our total magnetic field, cannot be equal to 0. So it means this option C cannot be correct. And now come we to the D part, that is option D. And in option D, it states that if I1 is equal to I2, then the Z component of the magnetic field at the center of the loop is minus mu naught I upon 2R. So it says that when I1 is equal to I2, Z component of the magnetic field is minus mu naught I upon 2 pi r. I think it is 2 pi r. 2r minus mu naught upon I upon 2r. So we are only interested in Z component, and we are given that we have once again wire 1 which is at x is equal to plus r, and current is along our I1, and that is our y unit vector, and we have our wire 2 which is at x equal to minus r, and we have a current which is our I2, and that is also in y unit direction. And circular loop is given as radius r and height I, and it is given that current is clockwise as seen above from above. And we have a circular loop, and for circular loop the radius is our capital R, and it lies in the horizontal plane, lies in the horizontal plane, which is given that z is equal to square root of 3 times r, and the center of this loop, it is given as 0, 0 square root of 3r, and current I, it is given as clockwise. And we are interested in only center of the loop. Here we are going to find out the particularly the z component. So we start with the loop, the magnetic field due to the loop having a radius r at its center. Magnetic field due to loop at its center. So we can write this as B loop, that is equal to mu naught I upon 2r. Therefore, and current is given as clockwise, and so we can say that the direction of this magnetic field will be along our minus z unit vector. So we can write this as minus z unit vector. Now let us find out magnetic field due to the wire. So we can say that magnetic field due to, first we start with our wire 1, and this wire 1 is x is equal to plus r, and obviously z will be 0 here, and the point which we are interested is, we can say, point of interest is our 0, 0 and square root of 3r. So we need to find out the displacement vector. So we have the displacement vector. Let us suppose we call this as r1. This will be equal to our minus of r, 0, square root of 3 times r. We are mainly interested in the perpendicular distance. So we can write the perpendicular distance from the wire to the point. From the wire to the point. Let's call this as r perpendicular. So this gives us our r square. It will be r minus 0 because x coordinate is 0, and then it will be y component is, both of y coordinate is 0, and then it will be square root of 3 and the component is 0. So this will be coming as 3r square and its square root. So this gives us as a 2 times r. So now we can easily find out the magnetic field due to a infinite state wire, that is our wire 1. You can say that magnetic field from an infinite straight wire at a perpendicular distance here we have said it as r perpendicular, and the general formula is it consists of angles also, sine phi 1 plus sine phi 2, but for infinite wire that phi 1 and phi 2 is our pi by 2, and normal formula is mu naught I upon 4 pi r, and 1 plus 1 is 2, so that gives us 2 pi r in the denominator. So we can write that the magnetic field will be equal to mu naught I upon 2 pi r perpendicular. So this gives us the magnetic field will be equal to mu naught I1, and this comes as 4 pi r. And for direction will be our positive z axis, z unit vector. Let me write it. This is our wire. So you can say B wire 1, and this is also B wire 1. Similarly, because everything will be same, only difference will be because the direction of the placement is at minus r. So because of this, the magnetic field will be in the minus z direction. So we can say similarly we have, because of wire 2, this will be coming as mu naught I2, we have here 4 pi r, and this comes as z unit vector, and this is a minus. So total field in the z unit direction in z direction. So we can write this as B total, which will be because of the loop plus because of the wire 1 plus because of the wire 2. And it says that the current I1 and I2 are equal. So we can say because of the because of the wire. Because of the wire, we can write this as wire 1 plus wire 2. We simply substitute their values. We get this as mu naught upon 4 pi r, and we get I1 minus I2, but it is said that current I1 should be equal to I2 in this particular case. So this gives us that B wire will be equal to 0. Therefore, B total is our only B because of the loop, and that is our minus v naught I upon 2 times r. So it means this option is also correct. This is correct option. So option number D is also correct. So the options correct are A, C and D. Now we come to the next question, and it was asked in the 2018 mains, and it states that an electron, a proton and alpha particle having the same kinetic energy are moving in circular orbits of radius Re, Rp and R alpha respectively in the uniform magnetic field B. The relation between Re, Rp and R alpha. So here we are given where R is the radius, and the standard formula for the radius we know is our R is equal to mv divided by qb, and it is given that they have the same kinetic energy. So we can write that kinetic energy that is our k will be equal to half mv square. From here we can calculate our velocity. So velocity will be equal to 2k divided by m and its square root. So therefore we can write that our radius will be equal to m upon qb and square root of 2k divided by m. So this gives us 2km and its square root divided by qb. Therefore, because the magnetic field and kinetic energy is same for all the three particles, so we can write our radius is proportional to square root of m divided by q, and we can use this relationship for all the three particles. So we start with electron. Now the electron mass, let us suppose that is me, and our charge is, that is our QE, is equal to E. So we can write that our Re is proportional to square root of me divided by E. Now we come to the proton. Proton, the mass is our mp, and charge, that is our qp, is also equal to E. And we can write that our rp is proportional to square root of mp divided by E. And finally we have our alpha particle. So we can write our alpha particle, so its mass, that is our m alpha, will be equal to 4 times mass of proton, and our charge, that is our q alpha, will be equal to 2 times the charge on electron. So once again our r alpha is proportional to square root of 4 times mp divided by 2e. So this comes as 2 divided by 2 square root of mp divided by e. 2 goes with 2, so this comes as square root of mp divided by e. Now we can easily find out the ratio. And one important thing is that the mass of electron is very much less than the mass of proton. Therefore, we can write that radius of electron will be less than radius of proton, but will be equal to radius of alpha particle. So the option number, you can say C, is the correct one. Option C is correct. We come to the next question. It was also asked in the 2018 mains, and it states that a dipole moment of a circular loop carrying a current I is M. It has to be separate. And the magnetic field at the center of the loop is B1. When the dipole moment is doubled by keeping the current constant, the magnetic field at the center of the loop is B2. Then the ratio of B1 and B2 is. In this case, loop is given, current is kept same between the loops, and dipole moment is doubled. So we have to find out how the ratio of the magnetic field is going to change. So we know the relationship, or we can say formula, that our dipole moment which is given as M is equal to current and area. A is the area of the loop, which comes as pi r square. A is area of loop, which is our pi r square, where r is our radius. And the magnetic field at the center of the loop at center of loop, that is our B, is equal to mu naught I upon 2r. And we already know that our magnetic moment is our I multiplied by pi r square. So therefore we can write that our r is equal to square root of m divided by I multiplied by pi. So therefore we can write our magnetic field B is equal to, we have this mu naught upon I, and this comes as 2 m upon I upon pi. And this can be further simplified. This will be coming as mu naught upon 2, and this will be coming as square and I cube. So this will be over I cube pi upon m. And it says that our current is constant. Keeping current is constant, and dipole moment is doubled. Okay. So from here we can say that our magnetic field is proportional to square root of m, and we can write it for two parts. We can write for our B1, which is proportional to square root of m1, and we can write it for B2, which is proportional to square root of m2. And we are given that the dipole moment is doubled, so that m2 is twice of m1. So we can easily find out ratio now. So where B1 upon B2, this will be our square root of m2 upon m1. m2 is our twice m1, so this is m1 and square root, m and m cancels out, so we get this as square root of 2. The ratio of b1 to b2 is square root of 2, so option number D is correct. Option D is correct. So these were 4 questions that were asked in the year 2018. 2 were from mains and 2 were from advanced. So this completes the questions. Thank you.